This is a video giving you some perspective on how you might think about a ball accelerating down a hill in terms of vector components. This word vector components, if it's not familiar to you, you should seek out some other resources that explain what a component is, because I'm not going to go through that in this video. But the idea is we already know that when something is in free fall, it is experiencing acceleration downward, and that acceleration has magnitude g. I'm going to go ahead and use g equals 10 meters per second, or meters per second squared. The difference between this and 9.8 is not significant. That's not where the challenge is here. So this is something that we're familiar with. When something is only interacting with the Earth, then it'll accelerate downward at this rate. But we can apply this idea to a situation where an object is actually rolling down a hill. When we have to deal with friction and like real world situations, then this approximation breaks down. But if you've got a really simple situation where something is just rolling down a hill and we don't have to worry about friction, we can look at it in terms of acceleration components. Here's what this looks like. I've got a hill, some kind of incline. There's an angle theta of the incline, and there is a height to that incline and a length. So if you imagine just like if I was to take this pencil and make a ramp out of it, then that ramp would have a certain length and would have a certain height from the ground. Those are important quantities because if we think back to our sine ratios, cosine ratios, etc., it's true that sine theta in this case is equal to opposite over hypotenuse, meaning the height over the length of the incline. I like to write L's like this, by the way, because it doesn't look like a 1. So this angle is going to be important in thinking about this perspective, but I'm going to do something weird because I want to examine how much of this acceleration is pointed down the hill. And in order to do that, I'm going to rotate my reference frame, and I'm going to take this acceleration vector and I'm going to draw it down here. So I know that this is equal to g. If the object was in free fall, this would be the length of the arrow. This would be the length of the acceleration vector. But I know that in this particular case, the object is not in free fall. It's accelerating down this direction. I want to draw this as a dotted line because I like drawing components as dotted lines. What I'm saying is there's a component of this downward freefall acceleration pointed down the hill. Now, if we're trying to complete the vector, there's also a component pointed in this direction, but this is kind of the point, is the object does not accelerate into the incline. That does not happen. It accelerates down the hill. So this acceleration that we're interested in over here has this value a. Now, you'll notice I've made a triangle here out of this vector, and the two legs are the two components. This I would call a parallel to the track. This symbol here means parallel. It looks like an 11, but that's not what it is. I'm saying this is the acceleration parallel to the track, along the track. And the tricky thing about this triangle is this little angle here is the same as that angle here. We can get into a derivation of that later, but it does work out. So that's actually theta. Interesting thing is I can say in this case it's still true because of this triangle that sine theta, sine of that same angle, is equal to this acceleration divided by my free fall acceleration. That is the opposite side, which in this case is an acceleration vector, over the hypotenuse, which is also an acceleration vector. It's the free fall acceleration g. Another way of looking at it, so this is one way of thinking about it with sines. Another way of looking at it is just thinking about the ratios of the sides of the triangles in both examples. The triangles mean different things. In this case, the triangle means the sides of, the height and the length of a ramp. In this case, the sides of this imaginary triangle are acceleration vectors, but the magical thing is it works out to actually think about them as similar. So I'm going to push this up a little bit. I'm going to say we have a ratio here of h to L, that is like shorter side of the triangle over hypotenuse of the triangle. And that ratio has to be equal to A parallel. Actually, I should make this A parallel as well, divided by the free fall acceleration g. Again, short side of the triangle, short like height versus short acceleration vector, and hypotenuse of the triangle, the length of that ramp itself and the free fall acceleration g pointed all the way down. A good way to check this to make sure that you know that it's true is imagine a situation where h equals L. So this is going to be our check. What if h equals L? Well, the only time that's actually possible is if the ramp is totally vertical, meaning the theta of the ramp is actually 90 degrees. So that height of our imaginary triangle, which isn't a triangle anymore, is equal to the length of whatever ramp we're using. If that's the case, if h equals L, h over L has to equal 1. And by this conclusion, acceleration parallel to the ramp is equal to the free fall acceleration. That is, acceleration in parallel to the ramp and g are the same value, just like h and L are the same value. This is a nice check because I've taken it to an extreme and I know that it works. I know that this can only work out if acceleration is g, and that's what we should see, because if we drop a ball here, it's just going to fall straight down in free fall. We could also do a check, I'll leave it to you to see how it would work, but what if h equals 0? What would that look like? What would acceleration have to be if the height of the ramp was 0? You probably already know the answer, but it's worth checking the math to make sure that it works out. In general, like looking at two different extremes for a situation can be a good way to see if your strategy is working out.